When we started the project, we had two challenges. One related to make it technical happen, but also to ensure that the machine during collecting of nodules would minimize impact on the environment. And this is where it really became interesting, having discussions with Dr. Clark on what are the requirements and most likely impacts on the environment, making sure you minimize disturbing seabed sediment and making sure that you minimize the intake of seabed sediment in the collection process. The buoyancy makes sure that the collector is able to maneuver on the seabed with a minimal disturbance on the soil, but still maintaining traction and maneuverability. And the machine itself, in air, weighed roughly 90 tons, but on the seabed, with the buoyancy applied, it was only 15. With the surface area of the tracks, you have a very low footprint, and you can still maneuver without making large footprints. And that is typically something you saw during the pilot, that it disturbs only the top layer, and after the collector has passed, in the post-survey you saw only small riffles of a few centimeters.
What we're trying to do on the seabed is reduce the footprint and the disturbance of the sediment. In the surface layers of the sediment, we have a lot of organisms live there, we have a lot of microbes live there, and if you disturb the structure of the sediment too much, then it'll take a long time to recover. So we want to be able to extract the nodules, but disturb those surface layers as little as possible. We see this when we look at the old technology that used the Archimedes screw, where it basically churned the sediments to a depth of about 80 centimeters. With our new technology, that disturbance is as little as 3 centimeters. It's really important to the microbes and the organisms that live in the sediments and to their recovery that we minimize the disturbance as much as possible. And the best way to do that is to minimize the footprint of the vehicle on the seabed by reducing its weight at the seabed by adding buoyancy to the vehicle.
The Coanda nozzle is a proven concept from the 70s. It was used back then, and I think the key element in using Coanda nozzle over a simple suction hose is that you minimize erosion on the seabed. By gently applying a flow over a curved plate, you can generate the suction force as required to pick up the nodules, but not eroding the top layer of the soil. And with that, you minimize the entrainment of sediment into the system, which has been a key focus from the start of the project. When we were discussing environmental impact, it was clear that benthic and pelagic plume would be important to minimize, and that starts with minimizing the intake of sediment at the pickup. We assessed the various options, quickly decided that Coanda nozzle had the best performance from that perspective, and then started developing the system with the prototypes following to make sure that we had the optimal shape and the optimal operating conditions for it.
A couple of the main impacts of our system are the formation of the benthic plume on the seabed and then the midwater plume at 2,000 meters. And our primary objective in informing the design has been to minimize the size of both of those plumes, because plumes have the potential to increase our footprint outside the directly mined area. The Coanda nozzles play a very good role. They're very efficient at picking up the nodules and minimizing the disturbance of the sediment. This minimizes the amount of sediment that goes into the collector vehicle, and it minimizes the amount of sediment that goes up the riser pipe to the surface vessel. So if we can leave as much sediment on the seafloor as possible when we're picking up the nodules, then there's less disturbance at the back of the vehicle, and the midwater plume is very small, and they're two of our prime objectives.
There are still opportunities to improve the performance, and that is focused on pickup efficiency on different type of nodules and the operating range where it needs to stay with respect to the sea floor. So we've been changing the shape a little bit and testing it again with prototypes at the lab environment to see if we could get the operating range to be a bit larger, and the result of that is lower intake of sediment.
When the Coanda nozzles pick the nodules up, there's a small amount of sediment gets sucked into the vehicle, and there's sediment attached to the nodules as well. And then they go through a series of pumps inside the collector vehicle into a big chamber that we call a hopper. And the hopper has differential flow rates inside it. And the nodules are turned and tumbled, and most of the sediment actually comes off the nodules at the seabed inside the vehicle. And because the nodules are a lot heavier, they sink to the bottom, and the sediment particles, 95 to 98% of them, actually remain suspended in the water that goes out the back of the vehicle. Allseas did a tremendous job doing lab trials with different flow rates and different pump sizes to actually optimize the hopper so that most of the sediment is separated from the nodules actually at the seabed. The small amount of sediment that does go up the riser pipe to the processing vessel are then separated again using the cyclones, and that remaining 3 to 5% is actually removed to the surface. That is then released into the midwater. But the most important thing is trying to keep as much of that sediment at the seabed as possible.
There is a Hopper 2.0 being developed and already tested to further improve the principles. But if there would be more time to settle, you would separate even more. So Hopper 2.0 focuses on enlarging the size of the hopper, just simple physical sizing, but also improving the time the nodules have to separate by improving the flow. And nothing is better than having very simple solutions having that much impact on the overall performance of the system. The diffuser is actually a device that returns excess water that was used to pick up nodules back into the environment. Flow we require to pick up nodules is significantly more than the flow we require to get the nodules through the riser to the surface vessel. So this excess water needs to be released again. And in this process, we can also make use of an opportunity to reduce the sediment again. So any sediment that was picked up in the nodule collection process, part of it, up to 95%, can be returned at diffuser level and doesn't enter into the riser system.
As the sediment's coming out the back of the vehicle, the diffusers play a role in concentrating and slowing down the flow, which stimulates the formation or promotes the formation of the gravity current. Now, the gravity current is where the mass of the particles cause the flow out the back of the vehicle to behave like a current that flows over the seabed, and it prevents most of the sediment lofting up into the water column, where it could be spread over large areas due to advection. And the benefit of that is that the area of seabed outside the direct mining area that's affected by sedimentation is greatly reduced, because the vast majority of the sediment, over 95%, is actually part of the gravity current that just flows over the seabed and follows the contours of the seabed and stays within a couple of meters of the seabed. And that's our goal, is to contain that benthic gravity current as low as possible and as localized as possible, so that the sedimentation footprint is contained to the smallest area possible.
During the pilot, we had a dewatering process at the surface vessel of one step only, consisting of a separator vibrating deck that had a lower cut level of 1 millimeter. But during the process, nodules get abraded a little bit, and we saw in the return water that we had nodule fragments below 1 millimeter. And what we're going to do on our commercial system is we're going to add one step in the dewatering process where we use hydrocyclones to filter out the abraded fines below 1 millimeter to ensure that the return water consists of sediment and water only.
A small amount of sediment needs to be released back into the environment. So it's separated from the nodules and then it's put into what we call a return pipe. And we've chosen to release that in our commercial system at 2,000 meters. There's been a lot of thought gone into that depth. It's a very strategic depth to release this midwater plume. And that's because most of the biomass in the water column is actually in the upper layers. So all the commercial fisheries, all the zooplankton that those fisheries rely on as part of the food web, they're all in the top 1,000 meters or so. So releasing that small amount of sediment at 2,000 meters bypasses the vast majority of the organisms and the biomass that's in the water column. The fact that the benthic plume forms a turbidity current that follows the contours of the seabed was a major finding. So we know that if we are mining on a slope, that turbidity current will flow down slope. The benthic topography is going to have to be considered when we do our mine planning. But what it does do, it means that we can actually predict where the sediment will end up with a high degree of accuracy. Basically, it's going to end up downslope, it's going to end up in the depressions. That was always a big unknown, is how far outside the mining area will these impacts spread. And knowing what we know now as a result of the information that was collected during test mining, we can answer that question with a high degree of confidence.
Our original mine plan is what we call straight line mining, where we try to drive as long distances straight, and then within the area we would like to operate, we're talking 80 to 100 kilometers, and then only once every few days make a turn and go back. But it comes with a price. If the collector drives in a straight line, the vessel needs to follow on dynamic positioning at the same pace, which takes quite some fuel. During the pilot, that maneuvering on the seabed is much easier for the collector. We made very sharp turns as part of the commissioning program, and as a result of that, you can decide to go for, instead of straight line, you can go for sweep mining configuration, where instead of the vessel following the collector, it stays stationary on top, and the collector does kind of back and forward sweeps on the seabed with sweep length somewhere around 500 to 1,000 meters.
One of the main findings from the collector test was that the currents at 4,000 meters behave very differently from the currents in shallower waters. So as we see in this model, there's more of a tendency to be, for the water to slosh back and forth rather than it being directional. And that was a major finding because in shallower parts of the water column, the currents are very directional, and that's why some of the models that have predicted how far the benthic plume would travel predict that it will follow the current.
It is known that over the year there is some variations on the subsea currents, and if it's like this, very stationary, we're good. If there would be a subsea current going into one direction in some part of the season, you can decide to mine upstream, and then the plume settles in already mined areas.